And it's a lipid protein combination, and it basically produces huge amounts of cytokine. So it's something that is of concern, but we don't talk about it very much. Now, this is really going to drive those who are not biologists a little bit crazy, but hold on for a second. Remember, here we had the lipid peroxidation, and this is where I really could use a pointer. But we had the lipid peroxidation as a result of the particle interaction with the cell. Now what that does is it causes an increase in calcium in the cell and the activation of an enzyme called PCPLC. And that we can do something about, at least not necessarily in you, but we can do it in a cell culture system. And that is, we can use agents that inhibit the lipid peroxidation or bind up the calcium inside the cell or inhibit the enzyme, this PCPLC. And when we do that, we stop the cytokine production. So here's the cytokine production again, stimulated by a particle. Here's what happened if we remove the hydrogen peroxide by way of a drug that is being used experimentally in clinical trials even for all kinds of inflammation. And then we have another agent that will inhibit that enzyme, and that also is a drug that's in clinical trials, but for treatment of cancer. And it supposedly doesn't do much harm to normal tissue. And then the last one is removal of the calcium, binding up the calcium with an agent that you wouldn't dare put in your body or you wouldn't be able to move. So, but in the lab we can use that in cell culture. And you can see that what we're doing is trying to figure out how this pathway works, okay? By using these different inhibitors of different steps that we propose. And of course, this is the whole pathway, and obviously, for this audience, I'm not going to spend really any time talking about the pathway, except to tell you that we have inhibitors that are in clinical trials for both of those two components. And so those are kind of molecules that are potential for treatment of those people who would be most susceptible. In other words, there may be something that comes out of our research someday that actually would help people living in this horrible environment, breathing in, particles. Okay, so now, one of the other things that goes wrong, as I told you in inflammation, is we get into our normal lungs. We have some macrophages sitting there protecting us all the time, and what we don't want coming in is the white cells from the blood, because that's inflammation. But that's what happens. See, what happens is they come in, and you notice everything turned green. You know, it's the color of pus. Not quite that bright. That's an enzyme released from the neutrophil. When it comes into the lung, it releases an enzyme called myeloperoxidase. And the myeloperoxidase generates a compound called hypochlorous acid. Now that doesn't mean anything to most of you, except if I tell you what the common name for it is. It's Clorox, okay? That's when neutrophils kill bacteria, they bleach them to death. And if neutrophils come in from the blood into your lung and they start releasing that, they're going to bleach your lung. And that's what happens. That's how you get damage, okay? And so this is not something we want to happen, and so we really need to find ways. So there are other things that we do, and that is that we have some adaptive increases in antioxidant enzymes and antioxidants, and these are enzymes that remove superoxide and hydrogen peroxide so that we don't make hydroxyl radical, and enzymes that make glutathione, which is a potent antioxidant. We can see that a whole bunch of different enzymes that are protective can be induced in our lungs by giving small molecules that are in small dose, do not cause harm but induce adaptation. Okay? So there might be some way of helping us protect ourselves, but I can tell you that it really doesn't work very well. It's sort of like putting up a shower curtain to protect you from a bullet. Okay? It might help a little bit in certain, in lung diseases and things, but when it comes to protecting you against something like cigarette smoke or protecting you against atmospheric pollutants, not going to really help enough. Okay? And then there's also actually a dark side to the antioxidants, because remember I told you that the oxidants are involved in your normal signaling in the cell. So if we all of a sudden put, and this is what would happen, basically things would start to go downhill if we have too much oxidation. But if we add in a large amount of vitamin E and vitamin C, megadoses as it's called, some people thought that would be protective. But what happens instead is that huge megadose depresses normal signaling. Okay? Which is not good. So, the basic thing to do is to have a normal diet, get your fruits and vegetables, get enough antioxidants that way, because you don't want to be deficient, because that's bad. But the megadoses won't help you. But some people have proposed something else. And hopefully this works.
To top up your omega-3 DHA, you could lead the life of the Inuit Eskimo.
Can you hear that?
Their omega-3 rich diet has contributed towards their healthy lives.
That's fish oil. What I say about there being a downside to everything. Okay. So David asked me to prepare a take-home lesson from all this. Don't go ice fishing is first one. Second is that oxygen is necessary, but it's an evil molecule. Cells contribute to production of reactive oxygen species in several ways. Iron is also necessary. Without it, we wouldn't have hemoglobin. We wouldn't be able to use oxygen to make energy in our bodies. We need iron in our metabolism, but it is the really bad player when it comes to particulates. Okay, it's the real thing that we have to worry about, most likely. Okay, so while damage can occur directly, the production of inflammatory mediators, inflammatory compounds, is a major danger. In other words, we have to worry about morbidity, sickness, more than we have to worry about mortality. One way of putting it is we get sick a lot more times than we die. And so you really have to be concerned about that. And so signaling for production of cytokines, as esoteric as it all sounds, is probably, and harder to understand, is probably more of an issue than, counting dead bodies or dead cells. Okay, and then there is some attempt of our bodies to attempt to adjust to oxidative injury, and where that figures in is in policy. We use the precautionary principle to try to make things as low as possible when we don't know how toxic something is. We try to get it down to zero. That's wonderful if we can do it, but most of the times, I'll tell you from sitting on the airboard, somebody's going to say, well, that costs the company more than 10% of their profits, and so therefore we can't afford to do that. Can't afford to impose that on them. Okay? All right? So we don't do it. But there may actually be some rationale for doing it too on a scientific basis. That is, that real low levels of ozone, or NO2, don't necessarily harm you. They may actually help you adapt to higher levels, okay? So we don't have to go to zero, all right? Which is something we have not done enough research into to understand what those levels really are, okay? So with that, I conclude, and I'll be happy to take any questions.
Thank you very much. Fascinating. So who would like to ask the first question?
Stunned into silence. There's one over there.